السلام عليكم ورحمة الله وبركاته أعزائي الطلاب، نسأل الله لكم الصحة والعافية. This is Dr. Abdulilal Shanable from Physics Department at Jordan University of Science and Technology, and our lecture today will be about elasticity, stress and strain. By the end of this section, you will be able to state Hooke's law, explain Hooke's law using graphical representation between deformation and applied force, discuss the three types of deformations such as change in length, sideways shear, and change in volume. Describe with examples the Young's modulus, shear modulus, and bulk modulus. Determine the change in length given mass, length, and radius. Elasticity. When a force acts on an object, the object may change shape by bending, stretching, or compressing, or a combination of all three shape change. A simple example here is a spring or a rubber band. On applying a force with our hand, we can change its shape, but when we remove the applying force, it goes back to its original shape. But what happens when the applying force increase or exceed the maximum limit? The object will start deform under the applied force, and at a certain point, the object will break or fracture. Elasticity of the human body. Many organs in our body are particularly elastic, such as heart, lungs, arteries, and skin. Heart is elastic organ to pump out the blood. Lungs need to be very stretchable when we breathe in. Elastic properties of the arteries are essential for blood flow. Loss of arterial elasticity may accelerate heart disease. Skin is also elastic. For example, a young person can go from 100 kilograms to 60 kilograms with no visible sag in their skins. However, elasticity of all organs reduces with age. Elastic mechanisms in animals. Wild animals have developed strategies to keep them safe from danger. These mechanisms are crucial to surviving in the wild. Here is a look at some defense mechanisms used by animals like balloonfish, spider network, and squid. Flexible electronics. Flexible electronics open the door to solar cells on a roll of plastic, smartphones, displays, and medical devices. Stretchable electronics, also known as electronic or elastic electronic. And these flexible electronics generally refers to a class of electronic device built on a conformable or stretchable substrate. And these devices will improve our health and lives in the coming years. Elasticity and Hooke's law. Look at this figure here. Here we have a vertically suspended metal rods. If there is an external force exerted on this metal rods, like an object with mass m hangs at the end of this metal rods, then the length of this metal rod will change by amount of delta L under the force of gravity, which is equal m times g. But what if the amount of elongation delta L is small compared to the length of the rod? Then we can write delta L will proportional directly to the applied force, and then we can write F will equal K times delta L. However, K is proportionality constant, and this is the form of Hooke's law. Look at this graph for a typical metal under tension. Here we can see the applied force, and here is the elongation delta L. At this graph we can see there is three regions: elastic region, plastic region, and the breaking point. However, at the elastic region before the proportional limit, this region is linear, and Hooke's law already be at this region. But after proportional limit and before the elastic limit at this region, the object will return to its original shape, but Hooke's law is not obey. However, after elastic limit, after this point, at the plastic region, the object will deform and will not return to its original shape. But after breaking point, the object will break or fracture. Beyond the proportional limit, the graph deviates from a straight line here, and before elastic limit, the object will return to its original shape if the applied force is removed. However, at the plastic region, the object is stretched beyond the elastic limit and remains permanently deformed at this region. At the breaking point here, as you can see, before the breaking point, the object will not return to its original shape and the maximum elongation is reached. And after the breaking point, the object will break or fracture. And at this point, the maximum force can be applied without breaking, and this is called the ultimate strength. Young's modulus. Here we have different factors can affect elongation of an object, such as applied force. The greater force means a greater elongation, and the other factor is material of which it is made. Is it made from iron or steel or made from copper? The other factor, dimension of an object, and here's dimension defined by length and the cross-sectional area of an object. Young's modulus can be written in a mathematical form as delta L equal 1 over E times F over A times L naught. Here's delta L is the change in length to applied force, and E is the proportionality constant and known as elastic modulus or Young's modulus, and its value depends on the material, and F the force exerted on the object, and A is the cross-sectional area of the object, and L naught represents the original length of the object. At this table, you can see typical values of Young's modulus for different materials, such as steel, which has 200 times 10 to the power 9 Newton per meter square, concrete, which has 20 times 10 to the power 9 Newton per meter square, granite has 45 times 10 to the power 9 Newton per meter square. What this means? This means marble or granite have less ability to elongate under the force exerted on the object compared to the brass or steel. However, liquids and gases don't have a fixed shape, so don't have these phases don't have the Young's modulus or shear modulus, as later we will discuss, but only have bulk modulus. Stress and strain, both concepts are related to the Young's modulus. Stress is a force per unit area and has a unit Newton per meter square. Strain is defined to be the ratio of the change in length to the original length, delta L over L naught, and has no units or dimensionless. Here we can compare between stress and strain. Stress is applied to the material by external agents or force, and strain is the material response to the stress. And we can rewrite the Young's modulus formula as F over A equal E times delta L over L naught, or we can represent Young's modulus E as stress over strain. Tension, compressive and shear stress. Look at this figure here. If we have a vertically suspended metal rod and this metal rod subject to an external force pulling this metal rod downward, but as you can see this metal rod is already in equilibrium, which means there is an opposite and equal forces if arise at the top here at the support balance the downward force. However, if there is an opposite and equal forces exert on an object, we call this a tensile stress. In general, there are three types of stress. The first one, tensile stress, material is stressed, and compressive stress, material is compressed, and shear stress, equal and opposite forces applied across its opposite faces, as we will see later. This is the tensile stress. As you can see here, if there is an opposite and equal forces exert on this object, and these forces lead to increase the length of the object by amount of delta L, we call this a tensile stress. But if these forces are opposite and equal and lead to decrease or compress the length of the object by amount of delta L, we call this a compressive stress. In the third case, as you can see here, if these forces are opposite and equal but also in parallel to each other, we call this a shear stress. However, the shear stress will not lead to change the volume of the object, but will deform the shape of the object by amount of delta L. This is dependent on the acting force. This is an ancient Greek building. As you can see here, these columns undergoes a compressive stress. The load on these columns arises from the weight of the roof. The force of gravity caused deformation of these columns over the years. This is the first example about tensile stress. One end of a steel rod of radius 9.5 mm and length 81 cm is held in a vise. A force of magnitude 62 kN is then applied perpendicularly to the end face at the other end, pulling them away from the vise. As you can see here, the external force exerted on this steel rod is equal to 62 kN, but also there is another force opposite to this force, which is the internal force arise at the vise. The first thing, what are the stress on the rod? As you know, stress equal the external force divided the cross-sectional area, which in this case equal by times r squared. The value of stress, which is equal to 2.2 times 10 to the power 8 Newton per meter squared. If we compare this result with the ultimate strength, as you can see here, this value is still below or less than the breaking point for the
structural steel. The second thing, what are the elongation delta L of the rod? You know that delta L equal 1 over E, which is the Young's modulus, times force divided cross-sectional area times the original length of the steel rod. From table 9.1, you can get the Young's modulus for steel, which is equal to 2 times 10 to the power 11 Newton per meter square. And then you can calculate the change in length delta L, which is equal 1 over E times the external force divided cross-sectional area times the original length L naught, which is equal in this case 0.89 millimeter. Finally, what are the strain of the rod? You know that the strain is the change in length divided the original length L naught, which is equal in this case 1.1 times 10 to the power minus 3. The second example, how much does your leg shorten when you stand on it? Calculate the change in length of the upper leg bone, the femur, when a 70 kilograms man supports 62 kilograms of his mass on it, assuming the bone to be equivalent to a uniform rod that is 40 centimeter long and 2 centimeter in radius. As you can see, only 62 kilograms of his mass exert on this bone. So we can calculate the force of gravity, which is equal m times g in this case, which is equal 607.6 Newton. And then we can calculate the cross-sectional area, which is equal by r square of this bone, which is equal 1.26 times 10 to the power minus 3 meter square. Finally, we can calculate the change in length delta L of this bone. So we will get 2 times 10 to the power minus 5 meter, which is equivalent to 20 micrometer. Shear modulus. As we discussed before, if we have opposite and equal forces in parallel exert on this object, then we have a shear modulus, and we can calculate the change in length delta L according to this formula. And here's G is the shear modulus. In general, shear modulus is 1/2 to 1/3 the value of Young's modulus. What happens if we have two objects with the different thickness, as you can see here in the figures A and B? If we apply the same amount of shearing force on both books, as you can see here, then the thicker object will shift or deform more compared to the thinner object in the figure B. The third example about shearing modulus. Find the mass of the picture hanging from a steel nail, given that the nail bends only 1.8 micrometer, given that the shearing modulus of steel is equal to 8 times 10 to the power 9 Newton per meter square. Look at this figure here. Here's the nail, and this is the length of the nail from the wall, which is equal 5 millimeter, and this is already given, and the diameter of this nail already given from the question, which is equal 1.5 millimeter, and this is before hanging the picture. But after hanging the picture, look at this figure here. This nail already bent by amount of 1.8 micrometer, and you can notice here the only force exerted on this nail is only the force of gravity, which is represent the weight of the picture. How to calculate the force of gravity exerted on this nail? We know that the cross-sectional area of the nail equal by times r square in this case, which is equal 1.77 times 10 to the power minus 6 meter square. And then we can calculate the force exerted on this nail. According to shear modulus, force equal delta L times shearing modulus G times the cross-sectional area divided the original length L naught. And we know that the change in length already is given 1.8 micrometer, and shearing modulus already equal 8 times 10 to the power 9 meter per Newton per meter square. And then we can get the force, which is equal 51 Newton, which is equivalent to 5.2 kilograms. So the weight of this picture is 51 Newton, which has the mass of 5.2 kilograms. The fourth example, which about shearing modulus. A horizontal aluminum rod 4.8 cm in diameter projects 5.3 cm from a wall. A 1,200 kilogram object is suspended from the end of the rod. The shear modulus of aluminum is 3 times 10 to the power 10 Newton per meter square, neglecting the rod's mass. Look at this figure here. The diameter of the aluminum rod is equal to 4.8 centimeter, and the only force exerted on this aluminum rod is the force of gravity, which is equal m times g. However, find the shear stress on the rod. We know that the shear stress is force divided the cross-sectional area, and the force here is the external force which arises from the force of gravity of the object, which has mass 1200 kilograms. And then we can calculate the shear stress, which is equal 6.5 times 10 to the power 6 Newton per meter square. Then the vertical deflection of the end of the rod, which represents the delta L. And we know that the delta L from the shearing modulus is equal 1 over G times F divided cross-sectional area times the original length L naught, which is equal in this case approximately about 1.15 times 10 to the power minus 5 meter. Bulk modulus. If an object is subject to inward forces from all sides, its volume will decrease. A common situation here is similar to an object submerged in a fluid. The fluid exerts a pressure on the object in all directions. The pressure is defined as force per unit area, and then we can calculate the change in volumes divided by original volume V naught, which is equal in this case minus 1 over B times the pressure, which is equal force per unit area, and B represent here is the bulk modulus, or we can rewrite this formula as bulk modulus equal minus original volume V naught times or divided change in volume delta V times change in pressure. And here negative signs means the volume decreases with an increase in pressure. As we discussed earlier, liquid and gases don't have fixed shape, so only the bulk modulus applies to them. At this table, you can notice that all gases have the same value of bulk modulus, which is equal 1.01 times 10 to the power 5, but are different for liquids. For water, equal 2 times 10 to the power 9, and for mercury, equal 2.5 times 10 to the power 9 Newton per meter square. Example number 5, which is about bulk modulus. A solid brass sphere is initially surrounded by air, and the air pressure exerted on it is 1 times 10 to the power 5 Newton per meter square, which is the normal atmospheric pressure. The sphere is lowered into ocean to a depth where the pressure is 2 times 10 to the power 7 Newton per meter square. The volume of the sphere in air is 0.5 meter cube. By how much does this volume change once the sphere is submerged? Look at this figure here. After we transfer the sphere from the air into ocean, the pressure will change, and also the volume of this sphere also will change, and we can calculate the change in volume according to this formula, where delta V equal minus 1 over B times delta P times original volume V naught. And then we can get that delta V equal minus 1.6 times 10 to the power minus 4 meter cube. And remember that bulk modulus here is for brass equal 6.1 times 10 to the power 10. Final example. Calculate the fractional decrease in volume for seawater at 5 km depth, where the force per unit area is 5 times 10 to the power 7 Newton per meter square. Given that bulk modulus for water 2.2 times 10 to the power 9 Newton per meter square. As you can see here in this figure, at 5 km depth we can calculate the change in volume delta V over the original volume V naught according to this formula, where the bulk modulus for water is 2.2 times 10 to the power 9 Newton per meter square, and the force per unit area in this case equal 5 times 10 to the power 7 Newton per meter square. And then we will find that the ratio for delta V divided original volume equal minus 2.27 times 10 to the power minus 2.
To summarize, at the end of this lecture, materials can be under tension, compression, or shear stress. If the force is too great, the material will exceed its elastic limit. If the force continues to increase, the material will fracture. Young's modulus applies for compression and tension, and the shear modulus for shear. Bulk modulus applies to an object whose volume changes as a result of pressure on all sides.